Benjamin-Ono equation, this m is the modular of the frequency. And for the Whitham equation, this is the symbol, right? Square of tangent, hyperbolic tangent c divided by c. So in particular for Whitham equation is the second type. In other words, it's a smoothing operator, right? So okay, so those are some common examples. You have a non-local symbol of m. Okay, so we are interested in periodical traveling waves. So it is a special solution of the form UC depending on x minus ct. So here c is the traveling speed and x is periodic. So if you plug this answers into the nonlinear equation, in the dual integration, you end up with this kind of a steady equation. Right? So here a is the integration constant. So for a solitary wave, this a will be equal to 0, right? But for a periodic wave, in general, you have to put in a constant there. So, so for the steady problem, actually, periodic waves are richer than solitary waves because now periodic waves, in general, is a 3-parameter family of solution. So you can choose the parameters to be the period, traveling speed, and this constant a, right? The 3-parameter family of solutions. And now let's look at the stability of this kind of traveling waves, periodic waves. So if you consider the perturbations of the same period, so this has been studied a lot in the literature, including Bernard. So we are not going to talk about this class of perturbations. It's studied more in the literature. So let's take the basic period to be equal to 2 pi. The minimum period is 2 pi. Now we assume this traveling wave is already proved to be orbitally stable under the perturbations of the same period in the energy norm. Right? So of course this is the orbital stability because this system is a translational imbalance. So usually we talk about this kind of orbital stability. So suppose we already know this traveling wave is orbitally stable under the perturbations of the same period. Now we are interested in the perturbations of different period or even localized perturbations. Okay, so so this kind of instability.
Zhiwu, can I ask a question?
Yeah, sure.
When you say the energy norm, do you mean the L2 norm or the norm defined by the Hamiltonian?
Yeah. So this is the energy norm, right? So there's two cases. If your M is a differential operator, energy norm is in the space H alpha over 2, right? If it's a smoothing operator, like the Whitham equation, then the energy norm is the L2 norm, right? Okay, so those are two different cases, right? Okay, so now let's look at this kind of so-called modulational instability. So it's also called Benjamin-Feir or sideband instability in the literature. Okay, so it's to study perturbations of different periods, or even localized perturbations. So for localized perturbations, I mean, you can think of the periodic waves is defined in the whole line, right? You just extend each wave pattern to infinity, right? You can look at the perturbations localized in the sense it's decays at infinity, right? For this kind of perturbation, we call it localized perturbations. Okay, now let's look at let's look at linearized problem. If you linearize the nonlinear equation around a traveling wave and in a traveling frame x minus ct and t, then you get the following linearized operator. So here I'm writing this so-called Hamiltonian form, right? So J is the partial X operator, and the L0 is a self-joint operator equal to M plus C minus F minus C. Okay, so the spectral problem of this perturbations, it could have different periods or even localized. So in general, if you look at any bounded perturbation of this operator, because now the coefficients are periodical in X, so let's say, we know by the standard flow case theory, you should look at the eigenfunction of the following form is EIKX, VKX. So here K is a parameter. We can choose it to be between 0 and 1, right? And VKX is 2 pi periodical. It's of the same period of the original traveling wave. So okay, so you look at this kind of broken form of the perturbation, right? Then if you look for a eigenvalue of the operator JL0, you plug this ansatz into the eigenvalue equation, eigenfunction equation. Then you can see it's equivalent to the following eigenvalue problem for Vk. And the operator becomes this Jk Lk, right? Jk is partial x plus ik, and Lk is mk plus c minus f prime uc. Mk is the Fourier multiplier operator with the symbol m c plus k, right? Shifted by k. Okay, so so we can see it's reduced to study the eigenvalue problem for a family of operators depending on the frequency k. Okay, now we say this operator UC is linearly modulational unstable. If you can find the frequency between 0 and 1, such that this operator JKLK is an unstable eigenvalue, lambda k, with the positive real part, right? So if you can find such an unstable frequency, so we say the traveling wave is linearly modulationally unstable. So this is the definition of linear instability. Okay, now let me make some comments on the results on linear instability. So first, if you look at the case when frequency is very small, right? So remember, if k is equal to 0, so this is sort of like perturbations under the same period. So we know this is a stable, right? We assume this at the beginning. Okay, so for k equal to 0, the spectrum of JL0 stay in the measuring axis. Let's say, and for this periodic problem, everything is discrete, right? So now if you look at a small k, for this case, you can it's not too difficult to prove. Actually, for small k, the only way to get the instability is by perturbing the 0 eigenvalue of JL0. You cannot get it from anywhere else. Okay, so this can be rigorous proof. Okay, so for k small, it's reduced to study the eigenvalue perturbation of the 0 eigenvalue of JL0, and the kernel, generalized kernel of JL0 is actually equal to 3. So the perturbation problem can be reduced to a perturbation problem for 3 by 3 matrix. Of course, it is not as trivial as it looks like, but it can be done quite precisely, especially if your traveling wave is a small one, is a perturbation of a constant solution. So this kind of perturbation can be studied explicitly for many cases. So this has been done by a lot of people, including Bronsky, Johnson, Whitham, Halakas, and a lot of other people. So they can find some explicit condition to ensure the linear instability for small k, in other words, for a large wavelength, right? Okay, so it has been done quite a lot. Okay, now I want to mention our results on nonlinear modulation of instability. Okay, so the linear instability means you can find a frequency such that the operator JKLK has an unstable eigenvalue, right? But how does this tell you the nonlinear dynamics? Right? So this is the question we want to answer. Okay, so our main result is the following. And for a large class of dispersive equations, including PDE, Whitham, BBM, Schrodinger, this kind of quite a general equations. Linear modulation of instability implies nonlinear instability for both multiple periodic perturbations and the localized perturbations. So now let's look at the precise meaning of this nonlinear instability. So for the multiple periodic perturbations, I mean you can find a integer Q and the theta zero strictly theta zero is a order one number. It might be small, but it's order one, such that for any x and any delta greater than zero, you can find a solution u delta tx to the nonlinear equation satisfying the initial perturbation u delta minus uc is small, is arbitrarily small than delta in the HS norm. It's a very smooth norm. And then later on, you see the orbital instability in the L2 norm at the time t delta. So t delta is over all the log of delta. So that means the growth is exponentially fast. Okay. So this is from HX. Initially, it's small in HS norm. And then later on, you see the growth in the L2 norm. So this is a strong sense of instability, right? Okay. So this is the multiple periodic perturbations. And the second part is for the localized perturbations. So we can find a solution U delta. Now, this is the solution to the nonlinear equation in the whole space. So it's satisfying the initial perturbation, U delta minus UC, is small in HSR norm. And later on, you see the growth in L2 norm. So this is the two results. And you see for the first result, for the multiple periodic perturbations, I use this orbital distance because if you look at the nonlinear equation, you make the period to be q times 2 pi. So this problem is still translation invariance. So it's more reasonable to look at the orbital instability. But for the second part, I didn't use this orbital instability because now if you look at the localized perturbations, you think of your traveling wave is your background, right? So if you translate the traveling wave, the difference will not be in HSR, will not decay, right? So in other words, if you follow the traveling wave in the traveling frame, and think of this as a background, then the perturbed problem is not a translation event. So that's why we didn't put the orbital instability there, right? Just the regular instability. There's a small difference. Okay, so this is the main theorem. Now, I want to discuss some main idea in the proof of this theorem. Okay, so and just one. Okay, so now let's look at. So first, let's look at a remark. So here, as I said at the beginning, so we're gonna look at both for two type of problems. One is M is a differential operator, right? So the other type is like a Whitham type of equation. So here M is a smoothing operator. So in this case, we need to put an additional condition, C minus the error infinity norm of F prime UC to be strictly positive. So this is sort of a technical condition to ensure the traveling wave is regular and also the unstable eigenfunction is regular. So just technical condition. But for the case when M is a differential operator, You don't need to add this assumption. Yeah, this assumption is also assumed in the literature to get the regularity of the traveling waves, to get the smoothness of traveling waves. Okay, so the proof of the nonlinear instability consists of the two steps. So first, we're going to study the growth of the semigroup associated with the linearized operator. So, and to get the growth estimate of this semigroup, we're going to use the Hamiltonian structure of this linearized equation for both periodic and localized perturbations. So in particular, I will use a sort of a general theory in a recent paper with Chung Zhang. So yeah, I will mention this in a moment. Secondly, after you get this growth estimate on the semigroup, then you need to worry about the nonlinear term, right? Especially for the PDE type of equations. The nonlinear term is the partial x of the FU, right? So you see there's a derivative there. So in general, if you try to close the estimate in, let's say in L2 norm, you end up with like a H1 norm, right? You cannot close it in a simple way. So this is a difficulty of loss of derivatives. So to overcome this loss of derivatives, so here we'll use a approach by first used by Grenier in this paper of constructing. So he first used this kind of idea to prove nonlinear instability of the shear flow for 2D Euler equations. So the idea is you can overcome the loss of derivatives by certain energy estimates. But because the energy estimate usually is very rough, so he used the idea of constructing higher order approximation solutions to compensate for the roughness of the energy estimate. Then combining these two, the loss of derivative can be overcome. So we'll look at the detail a little later. Okay, so now we look at the proof for the case when M is a differential operator. Okay, so so first let's look at the semigroup estimate. So for this one, I want to review briefly a general theory in a recent paper with Chung Zhang. So in this general theory, we want to study the following quite abstract and general linear Hamiltonian PDE. So it's of the following form: partial TU equal to JLU, right? So U is in a function space. So we call this space X to be the energy space. It's a Hilbert space. So the basic assumptions are first, the operator L generate a bounded bilinear symmetrical form. So sort of like L is a symmetrical operator. So it generates a quadratic form. So X is the largest space for this quadratic form to be bounded. Okay, then the main assumption is you can find a decomposition X into three parts. So one part is N. So this is sort of the negative directions of the quadratic form, and we assume this space N is a finite dimensional. In other words, you have a finite dimensional negative directions. The other part is the kernel of L. The zero directions, the degenerate directions. Then the rest of it is the positive space. So we assume the dimension of N is finite. And on a positive space, P there's a uniform positivity. And for the operator J, we only require this to be a still adjoint operator. So it can be quite general. So for example, J can be unbounded. It might not be invertible. It can be unbounded. Or it could have even infinite dimensional kernel. So this is a very general still adjoint operator. And also the third assumption is the range of L is closed. and also the kernel of L is contained in the domain of J. So like the regularity assumption on the kernel of L. Okay, so under these assumptions, yeah, we can get a whole bunch of conclusions. But one thing we're gonna need for this is instability stuff is the following: nonlinear instability stuff. We need to get the semigroup growth. So actually, we can prove the following so-called exponential trichotomy property. So you can break the energy space into three parts. We call it EU, EC, and EX. So EU is the unstable space. So it contains all the unstable eigenfunctions of the operator JL. And EX is the stable space. It contains all the stable eigenfunctions of JL. Right? And the EC, we call it the center space. Is associated with the spectrum in the imaginary axis. Right? So for this problem, the dimension of EU and the EX is going to be finite under the assumption H1 to H3. So the stable and the unstable eigenspace, actually, these two have the same dimension. And the dimension of the stable and the unstable space are finite. So EC is the finite codimensional space, is the infinite dimensional space. So first, these three spaces are invariant under the semigroup. And secondly, you can find a constant m and a constant lambda u such that on a stable space, we have a decay in a positive time direction. And on an unstable space, we have a decay in a negative time direction. And on a center space, you have a polynomial growth for any direction, t, right? And a polynomial growth, the power is at the most 2 times m minus l. So this is the semigroup estimate you can prove for this kind of very general Hamiltonian PDE. Okay. So the main difficulty in the proof is to get the growth estimate on the center space, because the spectrum on the center space might be very complicated, especially you might have a embedded eigenvalue in the continuous spectrum, and so on and so forth. So yeah, so this is actually the subtle part to get this kind of estimates. Okay, so anyway, so if we use this kind of general theory. And by the way, so as long as you get the exponential trichotomy in the energy space, if you also know your unstable and the stable eigenfunctions are in a smoother space, in a more smooth space, then you can lift this trichotomy to a smooth space. This can be done. And this is usually the case, right? Because you can usually prove for stable and unstable eigenfunctions, they have certain higher regularity, right? So you can push this trichotomy to be in a more regular space. Okay, so this is the abstract theorem I want to quote. Now let's look at the semigroup estimate for a multiple periodic case first. So by the definition of linear modulational instability, so first, you know, if you have one unstable frequency, then the nearby frequency are also unstable, right? Because if you JKLK, for JKLK you can find the unstable eigenvalue. Then if you change case slightly, yes, so this unstable eigenvalue is still there, right? You have this persistence. So in general, the unstable frequency is going to be an open interval, or several open intervals contained in 0, 1, right? So you can always pick a rational number in these intervals, right? So let's pick a rational unstable frequency, alpha 0, equal to p over q. So here p and q are two integers. Then you can see the Fourier form ei alpha 0x v alpha 0x now is of period 2 pi times q, right? It's 2 pi q periodic. Okay, so in other words, you can say the original operator, linearized operator JL0, now has the unstable eigenvalue in the L2 space of 2 pi q periodic functions. Okay, so we can consider the nonlinear instability of the traveling wave solution in a 2 pi q periodic space, right? Okay, now by using the general theory I quoted in the previous slides, you see, if you look at a semigroup ETJL0 in a 2 pi q periodic space, then you get this exponential trichotomy in any HS space, because the stable and unstable eigenfunctions live in regular, live in smooth function space. Actually, we can lift this trichotomy to any smooth function space you want. Okay, so and in particular, for a proof of nonlinear instability, you only need to get a certain upper bound on the growth of a semigroup. This follows directly from the trichotomy, right? Exponential trichotomy. So this is a very strong statement about the growth of semigroup, right? You can break into center space, unstable space, and a stable space. This is very useful if you want to control the invariant manifolds, like a stable or unstable center manifold. But here, if you just want to prove the nonlinear instability, this is a much weaker result than nonlinear invariant manifolds. So you only need a upper bound growth, upper bound of the growth of the semigroup. So is the following. So for any epsilon greater than 0, you can find a constant C depending on epsilon, such that the growth of the semigroup has this upper bound, given by E lambda 0 plus epsilon. So here, lambda 0 is the maximum growth rate of the most unstable eigenvalue in a 2 pi q periodic function space. So this follows immediately from the exponential trichotomy results in the previous slide. Okay, so this is the growth estimate we need for the nonlinear proof, for the nonlinear instability proof. Okay, now let's look at the semigroup estimate for the localized perturbations. So for the localized perturbations in the whole space, now we cannot use this general theorem directly, because now if you look at the operator JL0 in a space HSR, you see it does not satisfy the assumption there, right? In particular, because JL0 now have coefficients with 2 pi periodic. So if you look at a 2 pi periodic operator in the whole space, usually the spectrum, you have all this continuous. Even if you look at the operator L0 in the whole space, L0 now have a periodic coefficient. So if you look at this kind of operator, so if you remember the results for the Hiller's equation, right? You know, for this kind of second order ODE operator with a periodic potential, if you put it in a whole line, then you have all this continuous spectrum band, right? So in general, it's not true the operator L0 has a finite number of negative eigenvalues. In general, the spectrum will bend, right? So the assumption is definitely not satisfied for HSR space. So we cannot use this general theorem directly for the localized perturbations. But we make the following observation. For any function in HSR, by using Fourier transform, we can rewrite this function as a integral 0 to 1 ei cx upcx dpc. So here, upc is a 2 pi periodic functions in HS. So this is sort of like a integration in a frequency. Okay, so for any function you find in the whole line, you can always do this kind of decomposition. Then you can also prove the HS norm, HSR norm of U is equivalent to the integration of the UC the HST norm of UC. So you can prove is equivalent. Then to study the growth of ETJL0 U in the space HS. So if you use this frequency decomposition, you can transform into the estimate of ETJC LC UC, right? So this JC LC is exactly the operator we define when we look at the linear modulation of instability, right? So let me remind you the definition. So let me. Yeah, it's this operator. You see, JK is partial X plus IK. LK is MK plus C minus F prime UC, right? Okay, so these two operators, they are complex, but now if you put it together, you still have this Hamiltonian structure, right? So this is still at the joint. The other one is emission operator, right? So you can still have this kind of Hamiltonian structures. And then now for this operator JK is defined in a 2-pi periodic function space. So for this operator, it satisfies the assumptions in the general theorem I quoted, right? So in particular, this LK will have only finitely many negative modes, right? And all the eigenfunctions are discrete. So okay, so you see, we can use the general theory for the semigroup generated by JCLC in the 2-pi periodic function space. So then, if you know the growth of this semigroup, then you do the integration in the frequency. This will give you the upper bound growth of the semigroup in the HSR space. So this is exactly true as in this lemma, right? So you're still gonna get a so if you assume lambda 0 is the maximum growth rate of this whole family of operators for any frequency between 0 and 1. So you look at the most unstable eigenfunction associated with the most unstable frequency, and then use lambda 0 for the maximum growth rate. Then we can prove the semigroup defined in the whole space now has the upper bound growth, have the growth upper bound to be E lambda 0 plus any epsilon. So this is the upper bound estimate we need for nonlinear instability proof. Okay, now let's look at the proof of nonlinear instability. So we use the idea of Grenier in his proof of nonlinear instability of shear flows for the Euler equation. So the rough idea is you try to overcome the loss of derivative by using energy estimate, and compensate with this energy estimate. We construct a higher order approximation solutions. Okay. So first, let's look at the energy estimate we're going to use for this KdV type equation. So this is the version we're gonna need. So this is a nonlinear equation written in this form. So here UC is the traveling wave solution, and the capital U is a given function depending on t and x, and the capital R is also a function given. It also depends on t and x. So V is the solution of this nonlinear problem. So the initial value of V is equal to 0. And U and capital U and R are given. So, and we have certain a priori bound on capital U and V. Then, depending on this bound, so we have a certain have this kind of energy estimate. The growth of the partial t of VH2 norm is less or equal to some constant depending on beta of VH2 norm plus RH2 norm. So this is the energy estimate we're going to need. Okay, now to construct this higher order approximation solutions, we choose the integer n such that n plus 1 lambda 0 greater than c of 1. So c of 1 is the constant with beta equal to 1. Okay. So lambda 0 is the maximum growth rate. So the maximum growth rate might be quite small. But you can always choose an integer n bigger than that, such that n plus 1 times lambda 0 is bigger than c of 1, right? And we construct a approximation solution to the nonlinear equation up to the order capital N in the following way. So first, the first order solution comes from the most unstable solution associated with the most unstable eigenfunction. In other words, U1 is of this form, right? Vg is the most rapidly growing unstable eigenfunction, right? And the lambda is the most unstable eigenvalue. Okay, then we construct the U2, U3, so on and so forth by induction argument. So I will skip the details. So the induction argument will construct one by one up to any order you want, and such that for each j, you're going to have a uj hl plus 1 minus j norm is less or equal than cn e j lambda 0 t. So here L is 4 plus n. Okay, so the construction of this approximation solution is to ensure that the error coming from this approximation solution. So if this is equal to 0, then it's the exact solution, right? But this is only an approximation solution. So you're going to get the error term, RAPP, right? So this error term is going to satisfy the following growth estimate. So equal to delta E lambda 0 t to the power n plus 1. Okay. Up to this order, from t to t delta. So here t delta is such that delta E lambda 0 t delta is equal to theta, so sin theta less than 1. Okay. So you can see, roughly speaking, our error term is of the order theta to the power n plus 1, right? They quite small up to this time t delta. Okay, now let's look at the real error. You compare this approximation solution with the accurate solution from the nonlinear equation. So the initial condition is mu c plus delta u1, right? In other words, we choose the initial data to be perturbed around most unstable eigendirection, most unstable eigenfunction. So we want to compare the difference of U delta and U APP. Okay, now if you write this equation V, you see you can write it in this form. So this is exactly of the form in the energy estimate lemma, right? In this lemma, we study the solution V in this form, right? So okay, so if you use this energy estimate lemma, then you can get the following estimate. Okay. Now you see this RAPP H2 norm is controlled by delta n plus 1 times e to n plus 1 lambda 0 t. Okay, so if you choose n plus 1 lambda 0, n plus 1 times lambda 0 to be strictly bigger than C1, then by the Gromov inequality, you see this gives you the estimate for, give you the same estimate for H2 norm of V, right? It's of the same order as the RAPP, right? So in this way, we can close the estimate, right? We don't have any loose derivative. Okay, now the nonlinear instability follows very easily, right? You compare the nonlinear solution U delta with the Chern wave solution UC. You look at L2 norm. So by triangle inequality is bigger equal than these two, right? So for the first term, the leading order is given by the unstable eigenfunction. So you get a delta E lambda 0 t delta. And for all the other terms, it's at least the square, or higher order. So that's why if you choose theta to be small enough, then at the time t delta, you're definitely going to see the growth, right? Going to see go from the order delta to a order of theta, right? theta is a fixed number. So this gives you a exponential growth by this time. Okay, and from here you can prove orbital stability or orbital instability by some extra estimates. Okay, so this is a rough idea of the proving nonlinear instability for the multiple periodic perturbations. Okay, now let's look at the localized perturbations. For the localized perturbations, there's some difference. So first, unlike the multiple periodic case, now you cannot have any genuine unstable eigenfunction of this operator JL0 in the L2 space, right? So, the most you can have is this kind of flow case solution, right? It's not a decay at infinity, but you can construct a sort of a pseudo-globing solution, right? So you can do the following. So let's look at the most unstable frequency, C0, and let's choose a small interval centered at this most unstable frequency. And I is a small interval centered at this frequency. Then we construct the following initial data, initial perturbation. So is the integration in the interval I of EICX, VCX. So this VCX is the most unstable eigenfunction of the operator JCLC, or C in this interval I. Okay, and the unstable eigenvalue is lambda depending on C. Then, if you look at the linearized equation with this initial data, then you see the linearized equation becomes this form, right? And if you evaluate, so first this function U delta 0 now is decaying in HS space, in the whole space, and in the HSR space is finite. And if you look at the L2 norm of this UR, you see exactly has the order C times E lambda 0 T divided by certain factor 1 plus T to a certain positive power. Okay, so if you compare with the genuine unstable eigenfunction, you see now you have this extra factor 1 over 1 plus T to the power 1 over 2m. M is a constant integer. So this is still gives you some kind of growth because you see this is exponential growth. This is only polynomial. So this whole thing still grows exponentially fast. Okay. So by using this kind of ansatz and combining with the semigroup estimate in the HSR space, we can carry out the same similar proof as in the multiple periodic case. Okay. So this is the different thing with the with the multiple periodic case. You need to construct your initial perturbation by doing this kind of integration of unstable frequency. Okay, so this is the rough idea of proving this nonlinear instability theorem. Okay, now let me mention a few examples. So first, let's look at a fractional KDE equation. So here, this M is this operator, fractional derivative operator. So this alpha is a number bigger than half, and we use the power nonlinear term U to the power P, and for this kind of a fractional KdV equation, is proved. It was proved by Matt Johnson. You do get a linear modulation or instability if your alpha and P satisfy certain conditions. So our theorem will give you the nonlinear instability from this linear instability result. And the second example is the Whitham equation. Now this M is given by this symbol. Okay, so for this case, if you look at a small traveling wave solutions. First, this additional assumption is satisfied. So you do get a regularity of the traveling waves and the unstable eigenfunctions. And it's proved by Whitham and Matt Johnson. For the small traveling waves of a small period, we get a linear modulational instability. Okay, so theorem also apply to this case. Okay, now let's look at sort of a summary of this talk and some open problems. So first, so in this work, we can prove linear modulational instability implies nonlinear modulational instability for both multiple periodic and localized perturbations. If your model have a energy momentum function bounded from below. So for this, I mean, if you construct a KTV, if you construct a traveling wave solutions, usually the critical point of an energy momentum function, like energy plus c times momentum, is the speed. Okay, so if you look at the second order variation of this energy momentum function, together all with the L0 in my talk, right? This L0 is associated with a second order relation of the energy momentum function. Okay, so if this second order relational functional, if this second order relation of the energy momentum functional is bounded from below, so this will implies it has only finitely many negative directions. Then our theory will work, right? So it includes many models, as long as your energy momentum functional is bounded from below. Okay, now the remaining problem is for the case when the energy momentum function is indefinite. In other words, if you take the second order relation, it has infinitely many directions. It has infinitely many positive directions and also negative directions. Okay, so one important example is the 2D waterway equations. So for this case, the energy momentum function is known to have is unbounded from either directions. Right? Okay, and for this case, the linear modulational instability is quite a classical. Right? First obtained by Benjamin-Feir in the 70s. In 1967 for small amplitude Stokes place, and later it was proved by Bridges and Liao for the finite depth case. But for this case, to get a nonlinear modulational instability or nonlinear Benjamin-Feir instability, it cannot require some additional work. Okay, especially to get a semigroup estimate. Now it's different, right? Okay, and the other case, the other problem is if your model is linearly modulationally stable. In other words, for any frequency, it's always you cannot get any unstable eigenvalue. Then it will be interesting to prove nonlinear stability for localized perturbations. So this is the situation for many integrable PDEs. For example, the classical KTV equation. For this case, you have the linear modulation stability. Actually, if you look at nonlinear stability for multiple periodic perturbations for any multiple period, it was proved by Henry Martin for smooth perturbations, and by Bernard and Capitula for perturbations like in full space. But I think if you look at the perturbations localized in a space, like in H1R or H2R, the nonlinear stability is still open. Right? So finish it with these problems. Okay, thank you.
Questions?
Yeah. Any questions?
So So how hard would it be to adapt your machine to instead of having a KDV-like setup with your J being dx to a nonlinear Schrodinger equation type setup?
Oh, Schrodinger equation is easier because it's semi-linear, right? So for KDV equation is quasi-linear. So when we look at a nonlinear instability proof, we need to overcome this loss of derivative, right? So for Schrodinger equation, actually we included it in our paper. Yeah, this paper is almost finished under some final revisions. Yeah, we actually also mentioned KDV. It's more straightforward. You don't need to use this granular idea. It's a semi-linear, right? So you can close the estimate very easily.
For only for non-trivial phase, only for trivial phase solutions, or also non-trivial phase.
For what case?
So for the stationary solutions of nonlinear Schrodinger, there are there are the trivial phase solutions like Cn and Dn, and there are the non-trivial phase solutions which have a phase profile.
Yeah. So we only need a linear modulation or instability to get this nonlinear instability, right? So it doesn't matter whether it's a Cn or Dn, as long as you have a linear modulation and instability, then it implies it's nonlinearly unstable for both multiple periodic perturbations and local perturbations.
But so the solutions I'm asking for are not the Cn or the Dn solution, but the solutions that have a phase profile in addition to that. So for the linear stability problem is more complicated, right?
What profile? Yeah, can you repeat?
So these are the Cn and Dn solutions. They are real solutions of NLS with there's only a complex part that determines the time dependence, right? E to the minus I omega t times a real part, times a real solution, right?
Right.
The non-trivial phase solutions, the spatial parts can actually be complex.
Mm-hmm.
And then the linear stability problem is a lot more complicated.
Oh, okay. So you mean even for linear problem is not yet understood?
Well, I think it is mostly understood, but I think there would be some very interesting statements that could be made about. I'll send you a paper, but in terms of determining for which classes of perturbations, how many periods and so on, you would have stability or instability, non-linearly.
Okay, I see. Okay, yeah. Please send me the paper. Yeah. Yeah, but for this nonlinear instability business, as long as your energy momentum function is bounded from below, then you can always get it by using our approach. So yeah, even if your nonlinear term could have a derivative, because this energy measure is quite flexible. You can always overcome loss of derivative by doing this kind of energy estimate, constructing higher order approximation solutions.
Any other questions? All right, then thank you very much for the talk.
Okay.
I'll send you the paper, and thank you very much for this talk. And I guess I'll see you in a few months at Brown.
Okay. See you. Okay. Bye.
Bye-bye.
Okay.
Oh, Zhiwu, I got a question for you.
Okay.